Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tear, and this is video 5 in my new series on the Math Lovers book. And for those of you just joining me, I have a 3-volume series called the Math Lovers book that's available on Amazon in case you guys are interested in buying it. There's 3 volumes. Like I said, you can purchase each volume individually for $30 a piece in paperback or $9 in Kindle, or you can buy any combination. I recommend all three. The first book is more recreational. That's the one I'm going over now. This has 10 chapters on various areas of like high school level recreational math, which I think is kind of fun. And I think people who like math will think it's fun too, hopefully. My second volume is more academic. This is more undergraduate level. It has stuff like pre-calculus and calculus and group theory, some kind of, and anyway, that's a little more advanced. But the third volume is problems and solutions. So because there's exercises in each of these two books. Like I said, they're like textbooks, and so the problems and solutions manual has problems, and then solutions all the odd number problems. I think I should mention one more thing I haven't mentioned yet, and that's that the second volume, the end of the second volume, I have a section on the biographies of 80 famous mathematicians throughout history, and I think I will do some of those. I'll probably do those on a weekly basis, maybe starting tomorrow or in a few days. I'll do the first one. They're in chronological order, so that might be interesting to go over. Anyway, that's kind of an overview of the Math Lovers book, and today is, like I said, my fifth lesson, and today I'm going to be talking about the hexadecimal system of counting, also known as base 16. It turns out you can do arithmetic in arbitrary bases. I talked about binary or base 2 in my last lesson. Today I'm going to talk about hexadecimal or base 16, which, as you'll see, is also used by computers. It's pretty similar to base 2, actually, and it's very easy to convert back and forth between binary and hexadecimal because 16 is a power of 2. And that's also why it's used by computers, because computers, in their internal memory use binary, and it's easier to code in hexadecimal. You don't need as many symbols. So anyway, let's begin. So what is hexadecimal? Like I said, it's base 16, and just like any other base, the way that you convert from base 16 or hexadecimal to decimal is you have a number written out in hexadecimal, and each hex digit corresponds to a number from 0 to 15. It's a place valued system like binary and decimal, but now the places represent powers of 16. They're always powers of the base, which in this case is 16. So here's an example below. 49C3 in base 16. This is a hexadecimal number, and you'll notice that it has a letter as one of its hex digits, C. And the reason for that is since we're using 16 symbols instead of just 10, we have to have symbols for the numbers 10 through 15, which in decimal are 2-digit symbols, but in hex we write them as letters. So we write 10 as A, 11 as B, 12 as C. So you see the C represents 12 here. We go all the way up to F. F is 15. So that's how that works. So now let's convert this number 49C3, which is written in base 16, to decimal. Well, we just do it the same way as we would do any other base. So, you look at I guess there's four hex digits in this number. That means that the most significant digit, the one on the left, represent 16 cubed. So we have to do 4 times 16 cubed. That takes care of the 4. The next hex digit is 9, so we have to multiply that by 16 squared. And then C represents 12, so we have to multiply 12 by 16 to the first, or just 16, if you like. And then the last hex digit is 3, so we just leave that alone. 3 times 16 to the 0. And so now we just simplify this expression. 16 cubed is 4,096, so we take 4 times 4,096. We add 9 times 16 squared, which is 256. And then we add 12 times 16. And then we finally just add 3. So when you simplify all this, you can do the arithmetic yourself. You'll find the answer is equal to 18,979. So that's how you convert from hexadecimal to decimal. Pretty straightforward. I mean, it does involve a fair amount of arithmetic, but this is used by computers, and computers can do this very, very easily and very, very quickly. You just have to write the algorithms. So, anyway, that's how to go from hex to decimal. And now I'm just going to talk about how to go from hex to binary and vice versa. I mean, I don't even know if I do it the other way around here, but suppose we wanna convert the same number 4963, which is written in hexadecimal, to binary. How will we do that? Well, that's even easier because the reason that it's easy in this case is because it's very easy to go from hexadecimal to binary or vice versa, and there's a little table for doing that. What you can think here is that each hex digit 0 through 15 actually represents 4 bits. And there's a one-to-one correspondence between every hex digit, of which there's 16, 2 to the fourth, and every string of 4 bits. And you can think of it as counting in binary, going through them. So 0, for instance, represents 0, 0, 0, 0, 4 zeros in a row in binary. 1 is just the next number after that, which is 0, 0, 0, 1. You keep going, you just keep counting in binary. So 2 is 0, 0, 1, 0. Remember, 1, 0 is the next binary number after 0, 1 because there's no 2's in binary. So you keep counting like this, and if you do that, you'll get this table, which I show on top. And then now we have this table, and remember we have to use the letters A through F for 10 through 15. So now we can just use this table to convert from hex to binary, or we could go the other way around if we wanted to. So here's an example. Let's start with the same example we had before, 49C3 in base 16. How we convert that to binary? Well, we'll look at the 4 first, and 4 we see as 0, 0, 0, 1, 0, 0. So that's the first thing we write down. 0, 1, 0, 0, and then next to that is 9, which is 1, 0, 0, 1. So we write that to the right. And then C is 1, 1, 0, 0. So is that right? Or 1, 0, 1, 1, I guess. And then 3 is 0, 0, 1, 1. So now we get a string of 16 bits starting with a 0. But the last thing you have to do when you're done with this is you have to get rid of all the leading zeros, because no number in binary or in any other base ever begins with 0. So you just eliminate all the zeros at the beginning. So when you're done, you get this result. You get 1 0 0 1 0 0 1 1 1 0 0 0 0 0 1 1. You can check for yourself that that's the binary representation of 49C3 and hex. And I think I give one more example. Oh yeah, so now we're going the other way around. So let's do another example where we go backwards. So this time, and when you go backwards, I think you always want to, the first thing you want to do, you either want to partition your binary number into 4-bit substrings, because you always have to end up with 4-bit substrings. It's always easiest to start on the right. So I think we want to go from right to left here. So notice that the last 4 bits of this number is 0, 1, 0, 1. Well, now we can just look up in the table and we notice that 0101 represents the hex digit 5. So that means that our hex number ends with 5, and then we look at the 4 bits to the left of that, and that is 0100. That represents a 4, so that means that it ends in 45. And then we look at the 4 bits to the left of that substring, and that one is 1011, which represents a B. Then we keep going. The last one, you'll notice that there's only 3 bits left, 110. We really don't care. We could write it as 0110 if you like, and then you could use the table and see that that's 6. Or you could just note that 110 is 6 in binary. So the last hex digit is 6. So that means that the hex representation of this binary number we were given is 6B45. So that's how you convert between binary and hex. Pretty easy. And, converting hex to decimal is a lot harder. I did an example of that already, or going from decimal to hex. But you can kind of do it in 2 steps. You can always go to binary first and then convert to hex if you like. So, anyway, hexadecimal is a pretty convenient system. And like I said, it's used in computer programming a lot. So it's useful to know. Anyway, that concludes my video for today on hexadecimal representations and numbers. Thank you for watching. Long live math, and I'll see you guys next time. Bye.